Hey everybody and welcome, and in this video I'd like to talk about arithmetic and think about it really deeply. And with arithmetic we are focused on numbers, what they are, what they mean, and how they undergo different mechanical operations like addition, subtraction, multiplication, exponentiation, and division. And I throw in exponentiation even though many folks would teach it during algebra and don't put it as part of arithmetic, but I like it better to be taught in arithmetic so we can focus deeply on its fundamental properties, which you don't really do when you're thinking about algebra, to balance the two different subject matters in your head at the same time makes it difficult to really focus on exponents. So that's why I am integrating it in with arithmetic. But the first part of arithmetic is to understand the different classes we have of numbers. And the first one is natural numbers, which can also be called counting numbers, represented by this n here. And it's just 1 to infinity, every whole number. So 1, 2, 3, not in between 2 and 3, but 1, 2, 3, 4, all the way to infinity. Then the next level of numbers are called integers, and they're actually represented by a z. Not sure why it's represented by a z, but it is. And these are all the whole numbers along the number line. And you can think of a number line as, this straight line going from left to right. This is negative infinity, this is positive infinity, and let's say this is 0. It's going to be all whole numbers. So again, we're not doing any numbers in between 1 and 2 or between 4 and 5 or between -7 and -8. So only the whole numbers all the way to infinity and all the way to a negative infinity. These are called integers. The next level up are called rational numbers, and they are represented by a q. And I think the q in this case is to be symbolic of quotient. So when you deal with a fraction, you are dealing with a quotient, it's called. And a rational number is just a ratio of two integers. It's important to note that this is a ratio of two integers. As you'll see with the next class, this is important distinction to make. And so really a rational number is just any common fraction you might see, like 3 over 4, 7 over 8, anything with two integers acting as a ratio. The next class of numbers are called irrational numbers. And now these numbers have an infinite string of digits after their decimal point. They are commonly called pi is an irrational number. We have Euler's number E, the square root of 2, I think, or something like that. Square root of 2 is an irrational number, where really we're dealing with non-integers in a fractional matter. And this is what we are calling irrational. And these numbers are actually very useful throughout mathematics. And then we have the next class of real numbers, are called real numbers, and they are represented by this letter R here. And they are all the numbers we just talked about. And that just really what is a real number is just either it's a rational, integer, or a natural number. And so they're just really basically like a summary or breaking point before we move into the next class, which is imaginary numbers. And these are represented by the letter I. And these are just roots of negative numbers. So, -5, the square root of -10. And these are considered imaginary because we won't go into too much detail about them here, but these are what imaginary numbers are. And you could represent them by the letter I of 10, and this would be how you would write it. And then complex numbers are actually all of these numbers. All of these numbers are considered complex numbers because it's either going to have some real number A here plus some imaginary number here, A or BI. We could write that as A plus BI. And this is every single number, because if, let's say, the real number A is 0, we wouldn't see it, and we would just have this imaginary number I root 10 here, then it's still a complex number because 0 is still a number, and we have I root 10. So this is still a complex number, even though our real number is 0. And the same thing vice versa. If the imaginary number was 0, we didn't even have one, it'd still be considered a complex number. And those are the different classes of numbers that we have. And that leads us to the next part of arithmetic that's important to understand, is that we operate under a decimal system. And it's called a decimal system for a reason, because we have 10 digits that we use to represent every single number that we can make. And those 10 digits are from 0, 1, 2, all the way to 9. And so any combination of these digits, 0 to 9, can make up any number all the way to negative infinity and positive infinity. Now, it's no reason that we couldn't have used what is called a duodecimal system, which is where we would have used 12 digits instead of 10. So we have 0 to 9 here. We could have had 0, 1, 2, ... all the way to 12. And this 12 would be called 10, but it is, we would have went to, it would be a different symbol. So for example, they use these symbols here. I'll use alpha and beta as our symbols. And after 9, it would be alpha and then beta in the duodecimal system. And then what we would call 12 now would actually be 10. And obviously you can't use 10 as a digit, but that's the idea of a duodecimal system. And it gets really complicated and difficult to think about. It's difficult to conceptualize. However, there's really no reason we can't use any number of bases. Right now we use 10, but anything greater than 2, we really could have used as a base. We could use 50, we could have used 100. In fact, ancient civilizations did use this duodecimal system where they used 12 digits as their base. And all of this leads us to our arithmetic operations. And one last note is the reason we don't use Roman symbolism, like, X, V, I, is because as you get larger and larger numbers, we need new symbols. And so only a handful of people would know symbols once you get to numbers very, very large. And it would just be very difficult to use and standardize across. Well, it wouldn't be difficult to standardize, but it'd be difficult for people to know what symbol to use when you're dealing with numbers that are 10 to the, let's say negative 12 or 10 to the, 6. I mean, the number of symbols you would have to memorize would be just too much to handle. And that's why it's not optimal to use a system like Roman numerals. Okay, with that introduction, we can move into actually thinking deeply about different arithmetic operations. And the first one is addition. Really not too complicated or interesting beyond it being very basic. Obviously, an addition might be 1 plus 1 equals 2. And I think it's useful to think about numbers, even though they are an abstraction, they're really just an idea. We can think about numbers as objects. We often do this in real life. And so one object plus another object equals 2 objects. There actually is one cool aspect about addition, and I discovered this after I made the video, so I'm coming back and throwing it in here, is that this addition property might actually only apply to integers or our ideas uniformly, meaning 1 plus 1 is always 2 in the abstract, but there are scenarios when you add 2 objects, for example, sulfuric acid and water, where you actually don't get 2, for example. You get a diluted solution. You get something less than what you would get from 1 plus 1 equals 2. I just wanted to throw that out there. I thought it was interesting. The other interesting thing I could think of for addition was you might see the symbol quite frequently as you move up in mathematics. It is a sigma or fancy Greek S, and we use it to notate when we're trying to sum an expression. For example, I plus 4x, where I means index, and so we will start at 4. So I will be 4 for our first value. So we'll do 4 plus 4x equals whatever that would equal. And we would do this 5 times, and that's what this n equals 5 means. We will do this 5 times. And so you can see that here. So we have done this 5 times. And if you see any other variables or symbols that's not a number, such as x, you do not do anything with that x. You do not input any value for that symbol. You do not move it around or anything like that. You can even, after you've done all of the summation, you can even put a 10 in front or some constant in front, and that will scale your summation by whatever that value is. In this case, it's 10. And that's addition. So now we can move into subtraction, which gets much more interesting in my opinion, because now I want to think about negative numbers. So obviously you can have a basic expression like 3 minus 1 equals 2. But what if we had 3 minus a negative 1? So now we have an integer here. This actually equals 4. And you probably already knew that, but have you ever actually thought about why that is the case? The best way to think about it is you are actually removing a remover. We have an input here of negative 1 that makes this expression less if we left it alone or added it. But because we are removing this input of negative 1, we are actually making the expression output greater. We are removing a remover. Removing a remover. And this creates what we get here. 3 minus a negative value is equal to 4. And this even extends to multiplication. When we multiply, let's say 3 times negative 3, what do we get? We are actually getting negative 9. And how come this is the case? Well, we can think about it as we have negative 3 times. We are multiplying negative 3 times. And I have this visualization here. We have 3 objects, and when we say we are multiplying by 3, we're just adding 3 objects 3 times, and this gives us 9. But now we have this negative value here. We are removing a remover. And so, well, in this case, we actually aren't removing a remover. We are actually increasing the remover. So in this case, we are increasing the remover. We are increasing the remover, and so we get negative 9. Another way to think about it is imagine a number line. And when we were taking this negative 3 and we were increasing it 3 times. And so we have to go below 0. And we're going below 0, negative 3 more times, which gives us our negative 9. And so this is addition, subtraction, multiplication. These are the most interesting elements I could find that I wanted to explain. And then I think we can also conceptualize it pretty well with these visualizations. In this next part, I'm going to go to even more difficult concept to understand, and that's the process of exponentiation. And instead of doing it on a board like this, I already have pictures in my notes. So we will just look at my notes. Didn't really want to bring them over. So let's take a look at that. Okay, so up to this point, we've gone through addition, subtraction, multiplication. We've thought deeply about negative numbers and how if we are subtracting a negative number, in reality we're removing a remover. We are making the output greater by removing an input that made it lower. And we know that can get confusing, but hopefully I was able to explain it well. And that concept extends to multiplication as well. If you multiply by a negative number, I showed you the number line and how we went below 0 because we're adding a negative value. We are removing 3 objects 3 times, and so we are going actually less than 0, and so we get -9 if you do 3 times -3. And now we want to go to even more challenging concept to visualize, to really understand at a fundamental level, and that is the process of exponentiation. We are dealing with exponents. Exponents are notated a to the x power, you'll see here, and in using numbers it would look something like 3 to the 2, where a is 3, x is 2, and that's really the same thing as saying 3 times 3, so 9. If this was 4 to the 2, it'd be 4 times 4, and so on. Pretty simple, the notation's pretty straightforward. But when we really think about what it means and why we even have this notation, it can get complicated. The best way to think about it is when we're squaring something, we are actually dealing with squares. You can visualize squares. So 3 times 3 gives us 9 squares. But what's the base? What's the original number of squares used to give this output? We can actually find the inverse of this perfect square using a square root by performing a square root operation notated using these principal root here, as we can see. And this check mark looking notation tells us that we want to take the square root of our value 9 here. And all that is telling us is to go back to the original number of squares that made up this 9 if we were to square it. If we were to square that original number of squares, we get 9. And so we have our original here, and the square root of 9 is 3. So we're just doing the inverse. When we squared something, we took 3 squares and made it 9. When we take the square root, we took 9 squares and made it into 3. We are doing the inverse. But it's not always this clean. We're not always dealing with a perfect square. And that's when prime factorization comes into play. And we have prime factorization here. It's going to be difficult to quickly run through. Hopefully you've been exposed to it already and you sort of understand it. But when we think about prime factorization, we're dealing with a integer that's not a perfect square when we're trying to take its square root, meaning there wasn't a integer value that's going to be an output for a square root. We can't break 12 into some perfect amount of squares. So instead, we use prime factorization. We find what are the prime numbers that make up 12 that we can get to. And so 4 times 3 is 12, but we can even make 4 lower into prime numbers, 2 times 2. And then we can take that 2 out and move it outside of our root. And so our answer would be 2 principal root 3. Now, this is where it gets interesting. So we have our number 12. We are trying to find its square root. And so we can think about it as the 2 is the number of squares we need, and the length of each side is root 3. And by the way, 2 root 3 is 3.464, and this is going to, and so on, and many more digits, and this is going to be our area. The area of our original number of boxes is going to be 3.464, 101, and so on for a handful more digits. This is our square root. We take this value and we can represent it visually as such. We need 2 root 3s. We need 2 root 3s to make up one side. And of course, you know, squares have the same length on every side. And so we have our area being 2 root 3. And this can go on and extend to cube roots fourth roots, n roots, any number of roots you want to go to. And we can even find a to the negative x, so negative roots, which is really just 1 over a exponent. So a to the x, we could have did 1 over 3 squared, which is a to the negative 3. Just more ways to write it. And that is how we represent exponents. With that, we can move on to division. And I want to explain division by just telling a story where we have a guy named Numerator who always lives in the north. And when he is popular and more popular than his counterpart, who always lives in the south, and his name is Denominator. So we got Numerator and Denominator. When Numerator is really, really popular, everybody around them, all the numbers around them are scaling. They're getting bigger and growing. When Denominator is more popular than Numerator, everybody around those two people, those ratios, let's call them, they're brothers, everybody around them is doing less well. They're not as happy, and they're getting smaller and smaller. They're not able to scale. That is a fun way to think about division. Obviously, it's just a ratio between two quantities and that relationship between them, and they can increase in complexity as you move through your mathematical career. The last thing to touch on is order of operations. Mathematicians have developed a standardized order to perform these operations. So you would do any equation you have, you perform what is in parentheses first, and then you perform any simplification of exponents, any multiplication or division, and then you do any adding and subtracting. And now obviously this order is arbitrary. There's no mathematical reason you can't add before you simplify an exponent or before you multiply or divide. The key is you just need to put it in parentheses first to tell your reader, your viewership, to tell your audience that you want to add or subtract first. That is how we have decided to standardize our communication of our arithmetic operations. But there is no mathematical reason why you can't add or subtract before doing multiplication or division, for example. And with that, that's arithmetic. Hopefully, I did a decent job of diving deep into some of the more difficult concepts to understand, even when we're talking about something as basic as arithmetic that you learn when you're very, very, very young. All right, we'll see you in the next one.